Let's graph this exponential function. F of x equals 3 to the opposite of x. First thing we're going to do is recall an old exponent property. B to the opposite of n is really equal to 1 over b. Let me slow down. Why don't we split it up? Why don't I show you something a little bit different? Why don't I go b to the negative 1 and then raise to the n? And b raised to the negative 1 just means 1 over b to the first power. 1 over b to the first power, then raise it to the n. 1 to the n is 1, and then b to the n is b to the n. So 1 over b to the n. In short, what does that mean? B to the opposite of n is equal to 1 over b raised to the n. It says to take the reciprocal of b, which is 1 over b, and then raise everything to the nth power. Why don't we rewrite f of x using this formula? This is now 1 over 3 raised to the x. Now your base is between 0 and 1, which means this is an exponential decay. What's your horizontal asymptote? Your horizontal asymptote is simply y equals 0. And then let's pick some ordered pairs, x and then 1/3 raised to the x. So if you have x to be negative 1, take the reciprocal of 1/3, which means 3. And then 0, we get 1. And then 1, we get 1/3. I think that's enough for me to get this graph started. If you have graph paper, that's always handy. If not, just be neat. Draw everything, label everything. It's not a problem. Drawing is a mathematical skill. Labeling is a mathematical skill and a scientific skill. So always graph, draw, and label everything. What am I missing right now? I'm missing a horizontal asymptote. So I'm going to draw it right there. It is the x-axis. I'm going to relabel it. It's called y equals 0. And then here's your y-axis. Let's connect the red dots, and you'll see your exponential decay function. This function is decreasing from left to right. Now, if we do part B is a transformation of part A. It says take all the y values and make them their opposite. Okay, this says take the opposite y values from part A. Opposite y values from part A. So if you look at the opposite y values from part A, triple star here, I'm going to take that t-chart and relabel things. So x, and then the opposite of 3 raised to the opposite of x. We have negative 1, negative 3, 0, negative 1, and then 1, negative 1/3. And we simply plot this graph. If you're ever unsure of a transformation, don't worry, just pick more ordered pairs. Pick enough ordered pairs to help yourself understand how the graph is behaving. Once again, our horizontal asymptote is y equals 0. Dotted line there. Let's label certain things. So negative 1 to negative 3 here. 0, negative 1, the y-intercept, and then 1, negative 1/3, right about here. And you draw, this time, a increasing function from left to right, and it's actually a growing function. It's not growing exponentially, but it is a growing function where it approaches that horizontal asymptote. So what do you need to show you need to show all your labels, your horizontal asymptote, your labeled ordered pairs, and your graph. So that right there is all the evidence you need to show. Same thing over here. What evidence do you need to show? All your ordered pairs, your horizontal asymptote that's labeled, and your graph, and the arrows to match your domain and range. Translating the graph of a logarithmic function. Below is the graph of the natural log of x. Translate it to become the graph of y equals the natural log of x plus 2 plus 1. First thing you want to do is probably copy these graphs on a separate sheet of paper and make sure you indicate the arrows here. The other thing you want to do is label the vertical asymptote that was present. No computer program is going to do that for you. You must label as you practice mathematics, practice labeling, practice that mathematical skill. This is x equals 0. I'm going to go ahead and label this one as well, even though this is the second part. Once again, there is a vertical asymptote. So whenever you translate a graph or transform a graph, you're probably going to transform that vertical asymptote also. So that is x equals 0. Let's go back to part A here. Why don't I label this part A and this one part B? And we have the natural log of x, and then we are going to translate it. We're going to go left 2 units. This says left 2 units for x values, right? Left and right describes the x values. This plus 1 here says add 1 to all y values. Add 1 to the y value. So we only have one ordered pair, and let's concentrate on that. Let's make a t-chart with that one ordered pair from the natural log of x. That one ordered pair is 1, 0. And we're going to perform a translation to that ordered pair. Let's do it in this color. And what is that going to do? We have x is our input, but now we have the natural log of x plus 2, and then add 1 to the y value. So we need to go left 2 units. So that blue 1 is now a -1. And then for the y values, we got to go up 1. So this is going to be 1. For the most part, it maintains its shape. Now, where does the vertical asymptote go? The vertical asymptote is actually going to go left 2 units as well. So we're going to need a new vertical asymptote. Make sure you label that. So VA, x equals -2. Remember that your graph does not cross vertical asymptotes. Let's relocate -1, 1, and plot an ordered pair there. -1, 1, here we go. And we just draw the natural log function. If you're curious of the y-intercept, it is possible to find it. I'm just going to do some bonus material here. Y-intercept. How do we find a y-intercept? The y-intercept is when x is 0. So y is equal to the ln of 0 plus 2 plus 1. So there's our y-intercept. Y is equal to the natural log of 2 plus 1. If you translate your y-intercept as an ordered pair, it might be easier to see. It's actually x is 0, and your y value is, why don't I write it this way, y plus the natural log of 2. A little bit easier to read. And so there is your y-intercept if you're interested. What do you need for evidence of graphing here? You do want an ordered pair that's labeled, you want your vertical asymptote that's labeled, and you want your actual graph. So I'm going to circle my graph here. There's your final answer. Let's do the same for part B. Part B is over here. Let's translate to natural log of x minus 3 plus 4. This transformation here says go 3 units to the right. So let's go right 3 units. And then this transformation here says add 4 units to the y value. So if you add 4 units to the y value, that means you're going to go up 4 units. What happens to that ordered pair? What happens to the basic ordered pair of 1, 0? Let's see. We got to go right 3 units. So x is now 4. And then we got to go up 4 units. So it's 4, 4. And what is our output? Our output is the natural log of x minus 3 plus 4. So there's our chart. What happens to your vertical asymptote? That moves as well. The vertical asymptote moves what? Right 3 units. So relabel your vertical asymptote, which is x equals 3. And let's plot 4, 4. And let's plot our logarithmic function. Make sure you put arrows at the end of your graph. It has to match your domain and range. And then what are our final answers? We need a vertical asymptote. Make sure we label that. And we got to circle our ordered pair. It has to be labeled. And of course, circle your final graph. Let's graph some logarithmic functions. Let's call this one part A and call this one part B. And remember, with logarithmic functions, there's usually a vertical asymptote. We got to make sure we label that as well. And we should always talk about the domain. The domain is very, very important when we talk about functions. Notice the domain here is that x has to be greater than 0. We can only take the log of positive numbers. So the domain of g is simply 0 to infinity. And that also tells you your vertical asymptote. Your vertical asymptote is actually x equals 0. So let's circle that. We're going to need that anyway. We need to pick some ordered pairs, and we need some log properties to do that. You don't need a calculator for these problems. You just need to know that log base b of b is equal to 1. And that often helps. Another one you want to know is another log property that you want to know is log base b raised to the p power is equal to p. So both of these are really, really handy. Why are these handy? Well, let's look at g of 2. If you look at g of 2, what happens? G of 2 is equal to negative 3 plus log base 2 of 2. That's negative 3 plus 1. What's negative 3 plus 1? It's simply negative 2. So then you're starting to organize your values in a t-chart. X and, of course, g of x. So you have 2 and then you have negative 2. We need another ordered pair. Why don't we pick g of 1? G of 1, well, you should remind yourself of another property here. Log base b of 1 is equal to 0. So g of 1 is also very, very handy. We get negative 3 plus log base 2 of 1, which is 0. So that is now negative 3. So 1 and negative 3. And we have a vertical asymptote. So I believe that's enough to draw a pretty decent graph. Our vertical asymptote is at x equals 0. So let's label our vertical asymptote, dotted line there. X equals 0. we need to plot our ordered pairs. So we got 2, -2, and then we got 1 and -3. 2, -2, 1, -3, and it's approaching that vertical asymptote. Let's play connect the dots. Very likely the logarithmic function bends like that. Make sure you put your arrows at the end of your graph. It has to match your domain and range. And so notice your domain is from 0 to infinity. That does match. If you were curious, you could even look at its range. The range is what? The concept of negative infinity, and then it goes up to the concept of infinity. If you're looking at this sideways, if you turn your head 90 degrees to your left, you can see the range. And so the range of G is equal to negative infinity to infinity. You're reading the y values from bottom to top. That's how you get the range of G. It does say it's a graph. So our final answer is all your labels. Your vertical asymptote has to be labeled as well. Vertical asymptote is x equals 0, and then your ordered pairs have to be labeled, and then your graph has to be labeled. So there's your final answer. Let's look at part B. Let's graph the function f of x. We're going to do things in a very, very similar manner. Let's find f of 1/3. If you look at f of 1/3, we get 2 plus 1, which is 3. And then we need to find f of 0. I'm sorry, 0 is not a domain. Hush, hush. That did not happen. We do want to find f of 1. 1 is in the domain, and that is 2 plus 0, which is 2. We have enough there. Well, we need one more thing, and the other thing is the vertical asymptote. The way we get the vertical asymptote is to analyze the domain. We know that the domain of f, once again, we can only take the log of positive values, so it's going to equal 0 to infinity. And then we know our vertical asymptote. Our vertical asymptote is right there. Actually, vertical asymptote is x equals 0. We got enough evidence here to draw a really, really decent graph. Let's plot 1 and 2, and then we need 1/3 and 3. So 1/3 and 3 about here. And then we need 1, 2 right here. And we have a vertical asymptote. It's right here. Whoop. Didn't mean to color everything. Let's graph the vertical asymptote here. Vertical asymptote is x equals 0. Okay. Oh, I forgot to label my ordered pairs. Excuse me. Let's label them over here. X and then f of x. We said they were what? 1/3, 3, and then 1, and then 2. And let's draw our logarithmic function. This is a decreasing logarithmic function from left to right. Notice it approaches the vertical asymptote. You can see the domain is from 0 to infinity. You can see the range is from negative infinity to infinity. You can see its vertical asymptote because you labeled it. And then you labeled the ordered pairs that you plan to connect the dots with. Let's circle our final answer. Ooh. A biologist has a 1,371 gram sample of a radioactive substance. Find the mass of the sample after 2 hours if it decreases according to a continuous exponential decay model at a relative rate of 13% per hour. Let's translate our vocabulary. What is a continuous exponential decay model? And we're looking at the mass. The mass of this radioactive substance is actually decaying. So why don't we use the letter m for the mass of a sample? The mass of a sample is a function in terms of time. So we're going to say m of t is equal to the initial mass, symbolized by m sub naught, multiplied by base e, raised to a rate times time. We're actually given the initial mass. M sub 0 is equal to m of 0, and m of 0 is given. It was 1371. We also know the rate. We just need to rewrite that as a decimal. So 13 hundredths, decimal 13 hundredths. And we got everything. We also know the base is e in a continuous exponential decay model. It is a decay, so I need one more thing here. I need a opposite of r. That should be negative. Let's find our function. M of t is equal to 1371 multiplied by base e, negative decimal 13 times t. I'm going to circle this. This is really a key part of the problem. In many ways, it's more important than the answer. Now, because we have this, we could proceed to the answer. We need to find the mass of the sample after 2 hours. In other words, find m of 2. Now we have an expression, and we simply substitute 1371 e, negative decimal 13, and then multiply it by 2. Do your magic on your calculator. You should get this number, 1057 decimal 111724. Remember, when you evaluate this, make sure you use order of operations with your calculator. So I usually do the base e first and then raise it to the exponent and then multiply by 1371. We get this number here, and it says round to the nearest tenth. So 1 is less than 5, so we're going to round this number down to 1057 decimal 1. Let's write our answer in a complete sentence. The mass of the sample after 2 hours is 1057 and 1/10, I believe, grams. Yes, our units are grams. Don't forget your units. That's really, really important. Being a scientist or being a mathematician and translating languages, you got to remember your units. There's a big difference between kilograms and grams. Okay, or there's a big difference between a gram and an ounce. So make sure you label your units. The mass of a substance, which follows a continuous exponential growth model, is being studied in a lab. A sample increases continuously at a relative rate of 9% per day. Find the mass of the sample after 5 days if there were 618 grams of the substance present at the beginning of the study. First of all, we need to translate what a continuous exponential growth model is. And what is growing? The mass of a substance is growing, depending on how much time elapses. So our independent variable is time, and our dependent variable is mass. How do we write that into function notation? M of t. So with that function notation right there, it actually shows two variables. M of t is the dependent variable, and the independent variable is t. Very, very useful notation in mathematics. Now, it's an exponential growth model, so that means it's going to equal m sub naught multiplied by base e raised to the r, the rate of growth, multiplied by time. Now we're also given m sub 0, which is m of 0. M of 0 is equal to 618. We're also given the growth rate, r, is 9%. We just got to write that as a decimal. So write it as 9/100ths. Now we're ready to find our function. M of t is equal to 618 times base e raised to the 9/100ths multiplied by time. This is a very important step. It is more important than the answer. Mathematics is about modeling, especially with the use of functions. So let's box that function and let's take advantage of it. What does the function notation tell us? Well, let's go back and read what we're supposed to find. Find the mass of the sample after 5 days. So in function notation, that is actually m of 5. We simply evaluate this now for t equals 5. 618 times base e multiplied by 9/100ths times it by 5. Do your magic on a calculator. Make sure you use the order of operations. So I would do base e and the exponent first, and then multiply by 618. You should get this number, 969 decimal 2169306 dot dot dot. It says round to the nearest tenth, so we look at the hundredths place. It's a 1. 1 is less than 5, so we're going to round this down. We're going to round this down to 969 decimal 2. Write your answer in a complete sentence. The mass after 5 days was 969 and 2/10 grams. Don't forget your units. Make sure you know the difference between a kilogram and a gram. So when you're reading problems, even if you don't understand the English, go back and find the units in the word problem and then label your number. Very, very important. Let's circle our final answer.